Hello and welcome. So in this video, we are going to learn how to train a transformer model, especially a BERT model using MLM technique, which stands for Mass Language Modeling. Okay. So MLM stands for Mass Language Modeling. We use it to teach a transformer model like BERT to better understand a specific type of data or text of a specific domain. So what happens in MLM is that it takes some input sentences, masks a small percentage of the input tokens or input words, and makes BERT to predict those masked tokens. So to perform MLM on any kind of text or data, we will need the input text corpus, obviously, which will act like original labels to our masked words or tokens. It is really useful technique to get high accuracy on any kind of specific use cases. For example, the BERT is already pre-trained on a large amount of text, like it, like it has, I think, around 175 billion parameters. So using that, we fine tune it using the MLM technique on a specific kind of text that we require for a use case. And after fine tuning it, we can use it for any tasks like classification, sentiment analysis, and so many more. So without wasting any time, let's get to the implementation. So the first step is to install the Hugging Face transformers library. Okay. So I'll install pip install transformers. So after installing the transformers library, let's import all the necessary libraries that we will require. Import torch, and also from tqdm.auto import tqdm. Oops. Import tqdm. Okay. This will provide us with a beautiful progress bar. So next, from transformers import. What's happening with my import? Import Adam W, I guess. Yeah. So, and also the BERT tokenizer and the BERT for mass language modeling. From transformers import BERT tokenizer and BERT for mass LM. Okay. Next step is to actually create an instance of tokenizer and the BERT mass language model. So tokenizer is equal to BERT tokenizer dot from pre-trained. I'll be using the BERT base uncased model. Uncased. Okay, and next is the model, that is BERT for masked LM dot from pre-trained BERT base uncased model. And I'll just run the cells. Okay, form. Okay, it's from, not form. Okay, so now I have initialized the tokenizer and the model. So now I will be using a book dataset downloaded from the project Gutenberg. The name of the book is The Fireflower. It is just an example dataset to show you guys how to fine tune BERT on any kind of text corpus. Okay, so this is the dataset I have downloaded. So I'll just copy its path and I'll import it. Data path s and with, say, with open data path in read mode as f. Oops. Now data is f dot read dot split. Okay, and split on the basis of new line. Okay, so this is my data if you look at it. Okay, so we have quite a lot of zero characters values, right? So I'll say that let's print the length first. Print len of data. Let's see how many rows we have. Okay, we have 3949. Cool. Now what I will do is that I will remove that row which have less than 50 characters, all right, in order to delete the useless data, right? We had many zero characters data rows, right? So I'll say for sentence in data, whoops, in not in, I'll say that if len of sentence is less than 50, I'll say data row remove that sentence. Okay, I think that will work. Okay, cool. Now let's print the data. Print data, sorry, length of data. Okay, now we have 3078. Okay, now let's print the data and see if we had actually removed those single characters values. We have deleted them, but there seems to be another one. I don't know why. Okay, so let's just forget that. Cool. So the next step is to actually tokenize the data. Okay, the tokenization is a process which converts the words into tokens, right, or integer indexes. Okay, for that we will be using the BERT tokenizer. Cool. So I'll say inputs, what? Inputs is equal to tokenizer, and just pass your data. Max length, let's say 512. Truncation is true. Padding is true. And I want PyTorch, and I will be using the PyTorch, so I will be needing the PyTorch Tensor. So I will say return tensors is true. No, return tensor is PT. Sorry. Okay. Truncation true is not recognized. Okay. Oops, I missed the 9. I don't know what's happening today. Stop it. Okay, I'll run it again. Cool. Now I got the tokenized input. Okay. Now if I because it is a dictionary which gives us 3 keys and values. So it provides us with the input IDs, that is nothing but the indexes corresponding to those words. Token type IDs, just forget about this because we don't need it for this task. And the attention mask. Okay, the attention mask is basically there will be a 1 where there is word, otherwise it will be a 0 value. Okay, cool. Now to train the BERT model for mass language modeling, we will need 2 things: the input IDs, which will have a percentage of mass tokens, and the output labels, which will not have the mass tokens, that is the input tokens that were masked. So before masking the original input IDs, we will create a copy of input IDs which we will use as our labels later. So in order to do that, I will create a new key, let's say inputs of labels, which will be equal to the inputs of input IDs dot detach dot clone. So this is basically used in order to detach the input IDs from the PyTorch tensors. Otherwise, whenever we make changes to labels, it will automatically reflect changes to the input IDs also. So that is why we need to use the detach function and then clone it. Okay. Now if we print our inputs, we will have the labels also, which is just a copy of input IDs, okay, which we'll be needing for the output labels purpose. Okay. Now, to mask the input tokens, that is the input IDs, there's a rule that each token that is not a special token has a 15% chance of being masked. So, to create that 15% probability for each token, we will use the torch ran function to create a float tensor having equal shape of as that of input IDs. So, we'll create a random tensor torch using the torch ran function. Having the shape of the input IDs, okay, inputs of input IDs dot shape. So if we see the shape of input IDs, inputs of input IDs dot shape and random tensor dot shape. Oops, it should be random. So as you can see, it is both equal, right? Cool. Now if I print the random tensor, it's just in a matrix of random values ranging from 0 to 1. Okay. Now we need to give each of these float values a 15% probability of being masked. And we do that by creating a mask array. Let's say masked tensor is let's say if random tensor is less than 0.5. Okay, so wherever we will have true, for example, if I run this and let's say mask tensor, if I print the mask tensor, all right, so wherever we will have true, that value is less than 15% and it needs to be masked. But also we need to make sure that we do not mask the special tokens like CLS classification token, which is always at the first position of each sentence. Okay, like in this case, we should avoid doing this. It should be false. All right, we should not mask the special tokens that is done by the BERT model. Also, there are two other tokens like SEP model and PAT tokens. Okay, so for that we can do one thing is we can say that inputs input IDs is not equal to 101. That is the classification token. Also, so here 101 corresponds to the classification token and 102 corresponds to the separation token, okay, the SCP token, and 0 corresponds to the padding token. So this is the logic that I used to create a mask tensor that will avoid all the special tokens and only mask the other tokens, that is the 15% of the real tokens. Now if I run this, and now you will see these are set to false instead of true, like earlier it was set to true. Now after creating the mask tensor, next we will move on to next I will be getting all those indices from each row of my data which are set to true, that is masked. Okay, so wherever it is true, somewhere else there will be a true value. Okay, so I need to extract that index of that row, right? So for that I will say that non-zero indexes or indices, it's an empty list, So now I'll iterate upon the input IDs. Okay, so for I in range none of input IDs. Now I need the non-zero index value, all right, in the tensor. So for that I will say, now suppose I need the true value. Suppose this is my true value, okay, and I want this index. Okay, so what will I do that? Let's say must tensor of, let's say, index 0 if it has any true values, dot non-zero. So let's say what we get. So you can see that in the first row of this mass tensor matrix, we have 4 and the index value at 4 and 13 has value of true. Okay, that is our masked word. Cool. So but we need to flatten it. Okay, it is right now 2D array, so we need to flatten it. So for that I will use torch dot flatten. Cool. And now we need to convert it to a list and not a tensor. Dot to list Cool. Okay, so this is what I want to do, and this will allow us to store indexes of mass values in each of the row of our dataset of our mass tensor. So here will be I, and we need to append these values into a list that we defined above. Non-zero indices dot append. Cool. Now if we take a look at what we get. Okay, cool. So this is the indexes on which we have a true value. Okay, by true I mean that it is a mass value. Cool. I'll just clear the output. Now next thing is for us to replace these true indices values to the 103 token ID. Now by 103 token ID I mean the mask value, all right. So wherever we have true and we have got the indices, and we will replace it by the 103 ID, that is token. So I'll say that for I in range len of inputs of input IDs, I'll say inputs of input IDs and the ith row, and selecting the ith indices, right. This I represents the current row, okay, this one, and this represents the indices values, okay, in this indices. Cool. I'll assign it to 103. Okay, now if I print my input IDs, now you can see that wherever we had true, we now have 103, okay, instead of the actual token. Okay, 103 corresponds to the mask token. Cool. Now we need to process these tensors through a PyTorch data loader. So before that we need to convert this dataset to PyTorch dataset object. Okay, so for that I will define a class book dataset, which will inherit from torch not utils dot data dot dataset. Okay, now this is a really standard approach, okay, which is used in creating every dataset class of a PyTorch dataset, and it consists of a constructor init self. Here I will have the encodings, which represents our inputs. Encodings, and I'll assign it to self.encodings. Next function we need to include is that the length function, which will basically return us the length of our dataset. We'll simply return the length. return len of self dot encodings. And the last function we need to include is that the get item function. Self, and it requires an index. Okay, so now we will have the input IDs. Let's say we have the self encodings input IDs. And similarly, we have attention mask self dot encodings of attention mask. Let me check whether it is attention masks or masks. Attention mask, cool. Attention mask, and next is the token type IDs, which we do not require in this tutorial, but for the sake of standard approach, I will include it. Token type IDs. Next is the labels. Okay, now we need to simply return them with a single value. Okay, the indexed value. We will return a dictionary saying that input IDs is input IDs attention mask attention mask and token type IDs. Whoops, what happened? Token type IDs as token type IDs, and next is labels will be equal to labels. Cool. This was a dataset class. Now we can run it. Module has no attribute. What? torch.utils.data.dataset data done. Oops, lots of typos right now. Cool. Now we actually need to define an instance of the dataset class. So dataset look dataset, and here we will pass the data or the inputs, the encodings. Cool. Our dataset is ready. Now we need to define the data loader. So data loader basically allows us to yield the batch sequentially, right? So it will be torch.utils.data.data loader, and inside that we will include our data set. Next is the batch size will be equal to 16. That really depends upon you, how much RAM and GPU VRAM we have. Next is shuffle is equal to true. Cool. Now I'll run the cell data loader. It's a capital L, not a small l. Cool. So next we will define the device, actually on what device we should be training on. Okay, so we will say that device is equal to torch.device CUDA if torch.CUDA.is available, else torch.device CPU. Okay, so I'll print the device torch model.CUDA. Okay, sorry, it is device, not okay, cool. So right now I have the CPU version, but you can obviously change it to the GPU version. Just go to runtime and select change runtime type and select to GPU. But right now I won't do this, otherwise I will reset all the variables right now. So yeah. So next step is to push the model to the device. Okay, model.to device. So this is what you get after pushing the model to a CPU or GPU. So next step is to define some hyperparameters. I'll say epochs is 2 and optimizer is rmw with the model dot parameters and learning rate, let's say 1 e to the power minus 5. Cool. Okay. And next the main step, that is the training step. Okay. So before that we should tell our model that it is in the training mode. So for that we need to specify this one line of code, model dot train. Okay. Cool. You can ignore the output of this. Now the main thing, that is the training loop. So this is a really standard approach of writing a training loop for PyTorch for any dataset. So okay, let's continue. For epoch in range epochs, so loop will be a variable of tpdm data loader. So what this basically provides us with a cool looking progress bar of epochs and training, because we obviously need to know our progress of our training. And also it provides us with the batch, like I've defined here, batch of 16 right here. So it will provide the loop is of is containing of 16 batches. Okay, cool. So now I will iterate upon those loop for batch in loop. Whoops, I didn't require to run it. It was a mistake. So now we need to set the optimizer to 0 grad. So this basically ensures that our gradient optimization and the weights are set to 0 before training. And now we will take the input IDs. Input IDs is a batch of input IDs, and just make sure the key in this key should be same as this key. All right, the dataset you have defined. Cool. Input IDs, labels, batch of labels, and attention mask batch labels. Oops, sorry. Attention mask. Cool. So this is the 3 things we need in order to train this particular model. Next is the outputs that we will get from the model. Outputs is model, let's say input IDs and tension mass is equal to tension mass and labels is equal to labels. Cool. And then we get the loss, outputs dot loss. So this is basically a tensor, and inside that loss tensor we will have the loss value, okay, which we will get by the dot item function. So now we need to set the loss to backwards so that it will calculate all the gradient going in the backward direction. That is known as the back propagation. And now after the back propagation we need to update those parameters, the weights and biases. So that will do our optimizer, that optimizer dot step. Cool. Now for a cooler look we should set some description so that we get to know what we are doing with our model. Okay, so for that I'll say loop dot set under description, and I'll say epoch and dot format, oops, and dot format epoch. Okay, and next is loop dot set postfix to loss item. As I told you earlier that the loss, this loss is a tensor, okay, PyTorch tensor, and now we need the inner value of that. Okay, so we will get the inner value with the help of item operator. This is all we have to do for training our BERT for mass language modeling basically. Okay, so you can run this loop, and I hope this will be enough for this tutorial. So yeah, this was all for this video tutorial, and I hope you enjoyed it.